reaction in general. It goes back to the moles. The moles in the balanced equation. We're going to convert our masses to moles. We're going to look at the relative amounts of substances. It's got to go back to that balanced equation. The balanced equation is our recipe. Test hint number 19. Differentiate between theoretical and actual yield. This is just a definition question, and I went over that as I explained how to calculate percent yield. Actual is what we get when we do the experiment. Theoretical is what we get when we use the balanced equation and do our calculation. This will be a pretty straightforward question. Number 20, the relationship between theoretical, actual, and percent yield. Okay, let's think about when we've been in class and we've been conducting laboratory experiments and all those things that can go wrong. In every experiment we've done, I've asked you to tell me about sources of error. Reasons why your results might not be exactly correct. Okay, we got to consider those when we're trying to maximize our yield. We want to limit the sources of error as much as possible, reduce those down, mitigate the damages from that, so we get the best yield of product. So our actual yield is usually less than our theoretical yield, which means our percent yield is high, hopefully, but not quite 100%. Okay, the closer to 100% we get, the better. That takes us to the last 5 questions on the test, and it says calculate, calculate, calculate. Calculate moles, calculate mass, 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 and moles again. And I tell you in these examples what quantities will be given. We'll be given moles and a specific chemical reaction in the first one. So you will see something like this, a balanced equation. And I'll say, what if I said, in this balanced equation, what if I said we put in 10 moles of potassium chlorate and got out 10 moles of potassium chloride? How many moles of oxygen would there be? Well, you're all smart people. You clearly recognize that when I say we're putting in 10 moles of potassium chlorate and the coefficient is 2, that I just multiplied that by 5. I have 5 times as much. It's almost like doing the reaction 5 times. And I would get out 5 times as many moles of potassium chloride, so I would get out 5 times as many moles of oxygen. That answer would be 15 in that example. It's a very straightforward question just based on mole ratio in the balanced equation. Number 22, calculate mass when given mass, percent yield, and a specific chemical reaction. So this looks like it's just a mass-mass problem, but there's a little tweak to it. So let's say, in my example, we have 5 grams of potassium chlorate, and we want to know the actual mass of oxygen that is released based on a 75% yield. Okay, so you're like, sweet, I know how to do this. I'm going to put in my amount of potassium chlorate, I'm going to divide by molar mass, I'm going to follow that mole ratio, that 2 to 3 there, I'm going to figure out my moles of oxygen, I'm going to multiply by molar mass, and I'm going to find out exactly how much oxygen I should get. Okay, I'm just doing this off the top of my head, but let's pretend that we were supposed to get 100 grams of oxygen out of the reaction. Okay, we did the equation, where train tracks are mole tunnel. We're supposed to get 100 grams of oxygen. But the yield is only 75%. All I gotta do is take 75% of the 100 grams, or 75% of whatever the theoretical yield is, and go from there, and that tells you your actual yield. So it's solving for the actual yield variable when you know percent and you calculate theoretical. 23, calculate the mass when given the mass and a specific chemical reaction. Balanced equation already given. Remember, it won't be on the honors page. There'll be problems just like these in the short answer section on your honors page, but you'll have to write the balanced chemical equation first. And I love the honors page for this one because everything ties together. So by the time you're finished with it, you will know if you got it right. And most people usually get like 100% on this one. It's really awesome. So it's a mass-mass problem, and it is one where there's an excess reagent. so you don't even have to worry about the limiting reagent in this problem. 24, calculate mass when given moles and a specific chemical reaction. So that's an example where we're starting here already. You don't have to take that first number given and divide by molar mass to get down here in the mole tunnel, or do this first part of the train track problem, because you're already there. You already know moles. Start at the ratio step and go to the end. Okay? Watch the units carefully in these problems. If you're looking at the measurement units, you'll be able to easily work through these problems in just at the most a couple steps. And the last one, 25, calculate moles when given mass in a specific chemical reaction. So here's one where you're going to start with the initial mass, figure out how many moles of that initial substance you have, do the ratio, and stop. It wants moles of the new substance, not all the way to mass. The other things that you might see on an honors page, the other ways we can interpret these balance equations involve molecules or formula units. What if I said we put in 5 grams of potassium chlorate, and I want to know how many molecules of oxygen we get out? Is that a difficult problem? No. You're still going to start with the 5 grams, divide by molar mass, use the mole ratio, and instead of going to grams of oxygen, where else could you go? Well, pretty simple. You could come up out of the mole tunnel to representative particles, the rep parts, atoms, molecules, ions. And how would you get there? Instead of multiplying by molar mass, you'd multiply by Avogadro's number, 6.02 times 10 to the 23rd. If I told you how many molecules you had to start with, how would you get down into the mole tunnel? Well, you divide by Avogadro's number. And another thing we could throw in there, we chemistry teachers, would be, what if I give you volumes? What if this was a reaction that involved all gases? Or in this case, I could ask you for the volume of oxygen gas provided. So when we come up out of the mole tunnel there, we end in this last factor on the train track problem. Instead of multiplying by molar mass, we would multiply by molar volume, 22.4 liters per mole. Any gas at standard temperature and pressure takes up 22.4 liters of space. I've got a big black box over there out of camera view that has that on there as a reminder. And it actually makes the problem a little simpler because you don't have to go add up a molar mass of the substance. The molar volume is a constant for any gas, no matter what it is. And there we go. You might want to make sure that you know how to do your balanced equations, especially for the honors page. And then the key here is looking at the measurement units, taking your time, making sure you understand what the problem is really asking, and then it's just simple steps. Divide, ratio, multiply at the most. Good luck, happy studying. In the near future, you're going to have your final exam going on, so I hope you're watching these to help you prepare for your final exam as well. Good chemistry to you. Thanks, John.